Hello friends, welcome to our channel. In this video, we are going to cover about the suppression of drain-induced barrier lowering in silicon-on-insulator MOSFETs through source or drain engineering for low operating power system-on-chip applications. The name of our team is Thamirabharani and the team members are ANANDBABU, KATHIRVEL and HARISH. And we belong to Electronics and Communication Engineering Department at Tyagarajar College of Engineering, Madurai. Let's proceed further.
The design of the study involves an XMOS, extra polysilicon metal oxide semiconductor transistor structure, where the channel region is positioned between the top polysilicon gate and an additional bottom polysilicon gate. The bottom gate is symmetrically placed with respect to the top gate, creating a unique transistor configuration. The main parameter of interest in the study of the acceptor concentration N in the channel region and the thickness of the silicon layer TSI. The researchers use an analytical model to calculate the threshold voltage characteristics of the XMOS transistors, specifically focusing on long channel devices. By employing this analytical approach, they can estimate the threshold voltage for such devices efficiently and gain insights into their performance. For shorter channel cases, the researchers utilize numerical simulations with finite element method. This numerical approach allows them to determine the threshold voltages accurately while considering the impact of various parameters on device behavior. To ensure consistency and accuracy in their simulations, they ensure that the channel and source regions have the same potential. To make the calculations manageable and feasible, the researchers make several simplifications. They assume that the region in the transistor are uniformly doped, which simplifies the modeling process. Additionally, they neglect induced carrier charges during surface inversion, assuming a simplified scenario. Moreover, they assume that there are no surface states or fixed charge density in the gate oxide, further simplifying the analytical and numerical calculations. By combining the analytical and numerical methods, the researchers can comprehensively study the threshold voltage characteristics of the XMOS transistor. This research approach allows them to explore various design possibilities and understand the device behavior under different conditions, leading to potential advancements in semiconductor device technology. The design of the study involves nanoscale fully depleted silicon-on-insulator SOI CMOS devices with a thin silicon film body on a thick buried oxide BOX. The focus is on FD-SOI MOSFETs with thin silicon films of approximately 5 nanometer. The main parameters of interest are carrier energy quantization and threshold voltage control. These factors play crucial roles in the performance and characteristics of nanoscale FD-SOI MOSFETs. The researchers employ a methodology that includes quasi-2D analysis to gain insights into the subthreshold slope S and drain-induced barrier lowering DIBL in nanoscale FD-SOI MOSFETs. They specifically focus on identifying the leakage path between the front and back surfaces of the devices. By understanding these effects, they aim to optimize the transistor performance. To further investigate the performance and design options of nanoscale FD-SOI CMOS devices, the researchers conduct 2D numerical simulations using the MEDICI tool. This simulation allows them to analyze various performance parameters and understand the behavior of these devices under different conditions. Additionally, the researchers perform circuit simulations using the UFDG model in SPICE-3. These simulations evaluate the overall performance of the FD-SOI CMOS devices with a thin silicon film of a specific thickness EL is equal to 35 nanometer and the different circuit configurations. The SPICE-3 simulations help assess the potential applications of these devices for different circuit designs and purposes. Overall, the study aims to provide a comprehensive understanding of nanoscale fully depleted SOI CMOS devices with thin silicon films. The combination of quasi-2D analysis and 2D numerical simulations allows the researchers to gain valuable insights into the transistor characteristics, enabling them to optimize the design for enhanced performance and explore potential applications in modern electronic circuits.
The design of this study involves a retrograde channel doping the MOSFET with a special focus on optimizing the device parameters to minimize the short channel effects while maintaining a constant threshold voltage. The main parameters under consideration are the channel doping, the thickness of the lightly doped layer, and the heavily doped substrate doping. Additionally, the gate oxide thickness and the flat band voltage are the important parameters in this optimization process. The methodology adopted in this study revolves around maximizing the gate control to reduce the short channel effects. By iteratively optimizing the channel doping, lightly doped layer thickness, and heavily doped substrate doping, the researchers aim to find the most favorable combination of these parameters that result in a retrograde channel doping the MOSFET with minimal short channel effects. Contrary to the common belief that maximum substrate doping always minimizes short channel effects, this study explores the possibility of achieving the same outcome through strategic optimization of other parameters. The researchers also consider the subthreshold swing, which is an important factor in the device overall performance. They ensure that the increase in the subthreshold swing due to the optimization process remains within the acceptable limits. The optimization process in this study involves theoretical analysis and numerical simulations to assess the impact of different combination of parameters on the device behavior. By carefully tuning the channel doping, lightly doped layer thickness, and heavily doped substrate doping, the researchers aim to strike a balance that leads to superior device performance with reduced channel effects and a constant threshold voltage. Overall, the study aims to shed light on the importance of carefully optimizing various device parameters to achieve the desired device characteristics and improve the performance of the retrograde channel doping MOSFETs in nanoscale semiconductor technologies.
The design. The study focuses on N-channel transistors fabricated on silicon-on-insulator (SOI) substrates with N plus polygate. Two different silicon film thicknesses, 90 nanometer and 450 nanometer, are considered. Parameters: CIT, interface trapped capacitance, which represents the total amount of charge trapped at the interface between the silicon and the insulator layer. DIT, interface trap density, which quantifies the concentration of interface traps that can influence the transistor's behavior. The methodology that was followed was to analyze the transistor's performance. That subthreshold slope is calculated using formula SE KT by Q into ln of 10 of 1 plus CD plus CIT bar CJ. The depletion capacitance CD is thick film SOI transistors, depends on doping level NB, similar to bulk transistors. However, in thin film SOI transistors, the silicon film thickness can be smaller than maximum depletion width, leading to a smaller S value. The researchers validate their simulations through experimental measurements on transistors with film thickness of 90 nanometer and 450 nanometer. They also compare the threshold voltage between different film thickness. The Gemini simulation program is utilized for conducting the calculations and analysis. The design of the study involves investigating the inversion layer mobility in both N-channel and P-channel silicon metal oxide semiconductor field effect transistor MOSFET. The researchers specifically focus on the effective normal field and substrate impurity concentration as the main parameters affecting the mobility. The gate oxide thickness is also considered as an important factor in the design. The methodology used in this study revolves around the studying the relationship between MUFF and EFF in N and P channel silicon MOSFETs. The researchers identify a universal relationship between these two parameters, finding it holds up to a substrate impurity concentration of 10 per 18 centimeter minus cube for both electron and hole carriers. The dependence of MUFF and EFF reveals differences in behavior between electrons and holes. This understanding is crucial for optimizing the performance of N and P channel MOSFETs as it allows tailoring the device design to enhance carrier mobility. To further investigation, the factors influencing inversion layer mobility, the researchers explored the impact of substrate impurity scattering and surface roughness scattering on electron and hole transports. Both of these scattering mechanisms are known to affect their mobility and device performance significantly. To validate their findings, the researchers conduct experimental measurements and numerical simulations. The experimental measurements involve practical tests on fabricated MOSFET devices, providing real world data to validate the theoretical insights. Numerical simulations are also performed to complement the experimental results and gain further understanding on the mobility behavior. By considering gate oxide thickness and exploring various scattering mechanisms, the study contributes to a comprehensive understanding of inversion layer mobility in N and P channel silicon MOSFETs. The results enhance the knowledge of devices behavior, providing valuable insights for designing and optimizing the future semiconductor technologies. This understanding is crucial in the advancement of the performance and efficiency of MOSFET devices in modern technological applications,